So, I'm gonna get started. Your midterm grades were submitted this weekend, so you should be able to view your midterm grades at I think my.ccc.edu. I don't know exactly where they are. That's where I inputted them, so they should show up there. Let's see what else. Worksheets 2 through 5 will be due on the 6th of November. Homework number 3 will also be due on the 6th. And exam number 3 will be on the 6th. The semester project is due today. Get it in by the end of the day tonight. Yeah, the topic, sorry, the semester project topic. I may have just misspoken there. Just the topic. I don't need the whole project. That is not due until December. That was me misspeaking. Just the topic. I don't want to grade your project yet, so small. Your midterm grades are up. The semester project is due now that you know it's halfway. The semester project topic is due. The topic is due. Because we're halfway through the semester. I did just today notice that there was an issue with the slides for like chapters 3, 4, and 5 missing on Brightspace. I fixed that. That was clearly my fault somehow. I think I might have been trying to update them and accidentally deleted them or something. But they've been updated ones have been uploaded. So they should be okay. I will recheck them again after class today. But I did just upload revised versions of all the slides because I've been updating the slides. That's pretty much everything. We're going to continue on talking about plate tectonics and geology. We talked about diverging plate boundaries where new crust is formed last time. Now we're going to move on to converging plate boundaries where old crust gets destroyed. So divergent plate boundaries are where two plates are spreading apart. So molten rock comes up, magma comes up to the surface and forms new crust. Convergent plate boundaries are destructive margins. They're where two plates collide, are coming together, and generally one plate ends up subducting under the other, getting pushed down under the other plate. So the plates collide. If there's oceanic crust involved, then an ocean trench forms and lithosphere gets subducted into the mantle. So there are 3 ways that you could have convergent plate boundaries, depending on what the two plates that are colliding are made of. You could have oceanic continental convergence, where our oceanic plate runs into a continental plate, the oceanic plate sinks under the continental plate. Because the continental plate is thicker and less dense, so the oceanic plate will subduct under the continental plate. This is basically what's happening along the west coast of South America, and the subsequent volcanism forms the Andes. You can have oceanic plate convergence, where oceanic plate runs into oceanic plate, and whichever one is denser subducts. This tends to form volcanic island chains like Japan, the Aleutians, the Marianas, things like that. And then lastly, you can have continental convergence. In that case, nothing can sink because both are too thick and too light to subduct. So they crunch into each other, fold up, and form mountain ranges. So at an oceanic continental convergence, the denser oceanic slab will sink into the aethnosphere. Pockets of magma will develop and rise because this slab is sinking into the hotter aethnosphere. It melts. these pockets of magma develop, they rise up, and you get a continental volcanic arc forming. So some examples are the Andes, the Cascades in Washington and Oregon, and the Sierra Nevada mountains were all formed this way. So along the west coast of the Americas, there's a bunch of this going on. And so this forms what are called Andean mountain building, or mountains like the Andes. So here you have oceanic crust subducting under continental crust. You get a volcanic mountain arc. This example is in the Cascades. So in the Cascades, the Juan de Fuca plate is subducting under the North American plate, creating things like Mount Rainier, Mount Adams, Mount St. Helens, Mount Hood, those mountains. Here's Mount Hood in Oregon. Now, you can also have an oceanic-oceanic convergence, where two oceanic plates collide and one of them sinks under the other. This causes, so the two oceanic slabs come together, the denser one subducts. This will often form volcanoes on the ocean floor and can eventually build up to form volcanic island arcs. These are things like Japan, the Maldives, I don't know about the Maldives, the Aleutian, the Mariana, the Tonga Islands, Japan, lots of these island, probably the Philippines as well. These islands around the edge of the Pacific tend to be formed this way. So here are some of the volcanoes in the Aleutian chain. So the Aleutian chain is, this is the Pacific plate, and I think this is still the North American plate, I think. And this is the chain of volcanoes formed by this. These are various volcanoes. And where one plate subducts under the other, you get these volcanoes. And the last possibility is continental-continental convergence, where two continental plates come together. And in this case, neither of them can sink. This can produce new mountain ranges like the Himalayas. So this produced the Appalachians many, many millions of years ago, something like several hundred millions of years ago. So before Pangea, so Pangea, in the formation of Pangea, that formed the Appalachians. But the current case, that's the classic example, is the Himalayas or the Alps are both produced this way. The Himalayas is where the Indian subcontinent has slammed into Asia. It is still heading north. And so the material in between is folding and buckling and piling up. We'll cover that in more detail when we talk about mountain building. But this is the collision of the Himalayas of India and Eurasia. That formed the Himalayas. So we have a continental convergence.
The Himalayas, the highest mountains on Earth, contain 10 of Earth's 14 mountain peaks that are higher than 8,000 meters, or 26,240 feet. The other 4 are found in the neighboring Karakoram Range. The Himalayas formed following the breakup of Pangaea. 200 million years ago, India was located in the southern hemisphere, wedged between Africa and Antarctica. About 145 million years ago, India began to separate from these landmasses. During the next 80 million years, India moved more than 6,000 kilometers to the north. The mountain-building episode that generated the Himalayas began as India collided with southern Asia between 50 and 30 million years ago. Because India is still moving northward, albeit at less than half its pre-collision rate, the Himalayas are still rising. India's collision with southern Asia is shown here using simplified cross-sectional diagrams. The driving force was the subduction of oceanic lithosphere along the leading edge of the Indian plate. As the dense oceanic lithosphere plunged into the mantle, it served as a giant anchor pulling the Indian landmass along. Continued subduction created a continental volcanic arc along the southern margin of Asia. Offshore, an accretionary wedge was created, consisting of deformed sediments scraped from the descending plate and the remnants of the seafloor. By contrast, India's northern margin was a passive continental margin, consisting of a thick platform of shallow water sediments and sedimentary rocks. During the closing of the intervening ocean basin, the more deformable materials on the seaward edges of these two landmasses became highly folded and faulted. In addition, two major thrust faults, and many smaller ones, sliced through the Indian crust. Subsequent motion along these faults caused slices of the Indian crust to be stacked one upon the other. Today, these slices make up the bulk of the Himalaya's highest peaks, many of which are capped by tropical marine limestones that formed along the continental shelf.
So you can go to the top of the tallest mountains in the world and find marine fossils. So that was convergent plate boundaries, where two plates come together. And convergent, so divergent plate boundaries create new crust. Convergent plate boundaries generally destroy old crust. And this process of creating new crust on one side and destroying new old crust on the other drags the crust along like kind of a giant conveyor belt. Now, you can also have a third case. You can have the plates neither moving towards or away from each other, just sliding along. This is called a transform plate boundary. The motion is called shear motion or strike slip motion sometimes. So at a transform plate boundary, the plates aren't going towards each other or spreading apart. They're just sliding along next to each other. But they're big, huge chunks of rock touching each other, trying to slide. They stick. They have friction. So they grind past one another. No new crust is created or destroyed. But at these points, there's the potential for lots of friction. So there are a lot of transform faults that join various segments of the mid-ocean ridge. You have bits of divergent and then transform faults, allowing them to sort of be offset. That allows them to be not straight effectively. They join two segments of a mid-ocean ridge and they aid the movement of the oceanic crustal material. But there are also big transform boundaries. The most famous of these is the San Andreas Fault in California. That's where the Pacific and the North American plates are sliding against each other, rubbing away. The Pacific is moving roughly northward. North America is moving roughly southward relative to each other. So along the Mid-Atlantic Ridge, for example, see how these aren't like super straight? You get these, basically these little sliding gaps that allow the Mid-Atlantic Ridge system to be a little more flexible. So, this is the zone of drifting that accompanied the breakup of Pangea. And you have this thing where you have the transform faults in between connecting segments of the oceanic crust. And they allow it to be sort of, not so straight. So that's the most common place we find transform faults, but there are big ones that cover long distances, and those tend to have lots of earthquakes. So the San Andreas Fault, the one in Haiti, along the edge of Haiti, those are some transform fault boundaries. The transform boundaries are where they're sliding side to side. They're not going in, destroying crust, or spreading apart, creating crust.
Hi, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the relative plate motion that results in transform plate boundaries and the sorts of geologic phenomena we associate with those boundaries. Let's begin our discussion by taking a look at a classic location, Wallace Creek in California. Wallace Creek is the name of the little drainage here. I know it's dry at the moment, but when it rains, it does actually have water in it. And it drains across the San Andreas Fault. Motion along that fault has offset Wallace Creek along this central segment right here. You'll recall that the outermost rocky layer of the Earth's surface is broken into a series of slabs that we call plates, and these plates move around relative to one another. The boundaries between the plates come in basically three flavors. The plates can either be moving apart from one another, in which case we call them divergent plate boundaries. They can be moving towards one another, in which case they're convergent plate boundaries. Or they can be sliding past one another. In that case, they're called transform plate boundaries, and that's going to be the focus of this video. You'll notice that the example we just looked at, the San Andreas Fault, is a transform plate boundary shown on this map in green. Now if we zoom in on that situation, here's the west coast of North America, you'll see the San Andreas Fault is that central part of the map. And then up north there is a similar looking fault, the Queen Charlotte Fault, which is basically just a Canadian equivalent of the San Andreas Fault. The rock that is on the west side of the San Andreas Fault is part of the Pacific Plate, even if it's not oceanic lithosphere and is continental lithosphere like the Baja Peninsula of Mexico or the cities of San Diego and Los Angeles and most of the central California coast. On the east side of the San Andreas Fault is the North American Plate. San Francisco is just on the east side of the San Andreas Fault. It runs from the top of the Gulf of California up through central California and then offshore at Cape Mendocino. So this is Cape Mendocino up here. The sense of motion on the San Andreas Fault is right lateral, which means that North America is moving relatively to the southeast compared to the Pacific Plate, or another way of putting that is that the Pacific Plate is moving to the northwest relative to North America. These are not necessarily absolute motions, but they're just descriptions of plate motion relative to the neighboring plate. So that explains why we see what we do at Wallace Creek, that the offset appears to step to the right. So if we're standing, say, on the Pacific Plate side, as this picture shows, we've got Wallace Creek over here on the left, it picks up on the North American Plate side to the right. Now if we follow the San Andreas Fault up to where it runs offshore at Cape Mendocino, we see that there's another transform fault there, and this one is within the oceanic lithosphere, separating the Pacific Plate from the Juan de Fuca Plate. The Juan de Fuca Plate is a very small plate between the North American Plate and the Pacific Plate. So we're zooming in here on the Mendocino Fault in this central segment. And what's happening here is we've got a spreading center, so an oceanic ridge where new oceanic crust is being generated, basically making new Pacific Plate, making new Juan de Fuca Plate. But then because of the zigzag nature of the plate boundary, we end up having the Mendocino Fault accommodating differential motion between the Juan de Fuca Plate and the Pacific Plate. And that basically means that the two plates are scraping together there. So that brings us to this image in the book, the one that's designed to illustrate the concept of a transform fault. This is looking at a segment of oceanic ridge which has two plates. In this case, it's the African Plate and the South American Plate moving relative to one another. So basically, over time, the African Plate pulls away from the South American Plate, and as it pulls away, new oceanic crust is generated in the little gaps in between, like right in here. And you'll also notice that there's a portion of the plate boundary, like right here and right here, where the two plates are just scraping against one another. So there's grinding action there, earthquakes being generated as the two plates grind against one another. And that would be a nice example of a transform fault. So if we were to add some labels to that figure, we would see something that looks like the upper right of this image. You can see that these transform faults are what they're called when they're active, when the two plates are actively scraping against one another. And then once the new oceanic crust, say of the African Plate, which is generated at the ridge, clears the next segment of ridge, then the two parts of the plate are carried along at the same rate of speed in the same direction, and we just call it a fracture zone. So here's a little question for review. There was a really big earthquake in 2010 in Haiti, very close to the capital of Port-au-Prince. And you can see that that occurred along a transform plate boundary. This is the Enriquillo Fault, which is one of the faults that helps separate the Caribbean plate from the North American plate. And you can see that the sense of motion here is left lateral. So if you're standing on the Caribbean plate looking north at the North American plate, it looks like the North American plate is moving to your left. So keeping in mind the lessons of Wallace Creek, what would you predict for changes to the shape of the island of Hispaniola and the nation of Haiti, given geologic time operating on this fault? If you said that you would expect the coastline of Haiti basically to move this way over time, or that this long peninsula basically is going to move towards the east over time, then congratulations, that's the answer that I was fishing for. Thank you very much for your attention. This has been a Smart Figure.
So let's talk about how plates and plate boundaries change. Plates and boundaries can migrate, they're created, they're destroyed. Plates can basically collide and stick and merge together. This is basically what's happened with Europe and Asia. They used to be separate plates. They're now one big plate, Eurasia. So for example, and the boundaries can move around. So the breakup of Pangaea occurred as a new ocean basin formed, the Atlantic. You could have new rifting zones form and separate off new plates, basically. This didn't occur all in one time. The plates will continue to move over time. We don't fully understand the forces exactly that drive them, so we don't have the best predictions of them. We can assume they're going to more or less go in the current direction they're going for a while. But since we don't fully understand all the forces involved in the currents in the mantle that drive the motion, it's hard to tell if they're ever going to stop or maybe turn around or things like that. We know that's happened in the past because we can figure out how things have moved in the past, but it's hard to figure out exactly how they're going to change in the future. So the breakup of Pangaea looked like this about 200 million years ago. It started to, the first major event was the separation of North America and Africa, which marked up the opening of the North Atlantic. This was followed by the opening of the South Atlantic, the separation of Africa and South America, and India, Australia, and Antarctica separated. About 50 million years ago, Southeast Asia docked up with Eurasia, while India continued its northward journey, and by 20 million years ago, India had collided with Eurasia to create the Himalayas and the Tibetan Highlands. And in the past 20 million years, Arabia has separated from Africa, creating the Red Sea, while Baja California separated from Mexico to form the Gulf of California. So how did we test this plate tectonic model? How did we begin to understand how it actually worked? Well, after World War II, we really started to study the ocean floor a lot more. So some of the most convincing evidence confirming seafloor spreading came from drilling directly into ocean floor sediment and dating it. We found that the age of the deepest sediments was surprisingly young, and that the thickness of the ocean floor sediments verifies seafloor spreading. The sediments are thinner near the oceanic ridges, the spreading zone, and they get thicker as you move away. So we see as you go from the seafloor spreading, basically seafloor here is younger, and it gets older and older as we travel away. So we find that the Atlantic Ocean is all less than maybe 180 million years old. We can also look at mantle plumes and hotspots. So we talked about volcanic islands. You may have noticed I didn't mention Hawaii, because Hawaii is in the middle of an oceanic plate. It's actually caused by a mantle plume, which is a hot upwelling of magma that rises up and hits the plate above it. and then it can cause volcanoes where it hits. So these rising plumes of mantle material, and what happens is that because the plates are moving, they move on top of these plumes of mantle material. And they basically leave behind a trail of volcanoes, old dead volcanoes. So volcanoes can form over them, and they form what's called the hotspot tract. So in Hawaii, the current hotspot is under the big island of Hawaii. As you go along the islands of Hawaii, they get smaller because they're actually older and more eroded. But if you keep going, there's actually a whole long chain of underwater mountains called the Emperor Seamounts that continue on from Hawaii. So you get these hotspot volcanism, you get extinct volcanoes, which eventually erode down. So, you know, Hawaii is been actively is, you know, the age is about 0.7 million years to the present day. There's active volcanoes making new land on Hawaii right now. Maui is less than 1 million years. Mokalaki is about 1.3 to 1.8. Oahu is 2.2 to 3.3. Kauai is 3.8 to 5.6. And then, you know, so this is Hawaii. And then there's like a chain of underwater mountains that you can track all the way back to Siberia, where this hotspot used to be, where were these massive, the Siberian traps, which were these massive volcanic events that happened long ago. There are other hotspots out there, like the one under Yellowstone. Yellowstone is also powered by a magma plume or a hotspot. But the best evidence for seafloor spreading is paleomagnetism. This is an ancient record of the Earth's magnetic field preserved in rocks. So we can see a few different things. One thing we can observe is that basically when rocks form, they solidify, and they trap magnetic materials, lock magnetic materials into place. Magnetic minerals like magnetite or hematite or things like that. And these minerals record the magnetic field of the Earth at the time they were formed. So by studying layers of rocks or rocks through history, you can get a record of the history of the magnetic field of the Earth from the point of view of where you are. So one of the things you can look at is how the magnetic pole moves. Because the magnetic pole wanders around, it moves. And we know this because we can watch it moving right now. Like, you know, it's something you have to correct for. It's steadily moving around. One of the interesting things is that if you look at the record of the movement of the magnetic pole in Europe and in North America, they tell you the pole was in different places. The solution to this is if they have moved from where they currently are and moved relative to each other. Another thing is that Earth's magnetic field reverses every once in a while. And this is recorded in rocks as they form in the oceanic ranges, leaving a pattern on the seafloor that records these reversals. And it's symmetrical on either side of the ridge. And you have normal, then you have reverse, then you have normal. It's like a barcode, and it mirrors each other on either side of the ridge. So the apparent polar wandering path, if you look at the position of the pole for Eurasia, it moves like this over the last 500 million years. And this is the one for North America. You'll see how they don't match. But if you add in the expected movement of the continents, they end up matching each other. So you can correct by actually allowing the continents to move, because that changes where you're measuring the magnetic field from. So where the pole is relative to that rock will be different. So over time, every million years or so, you will have a reversal of the magnetic field of the Earth. It just happens every once in a while. So, at 0.4 million years, it's normal. At 1.2 million years, it's reversed. At 2.6 billion years, it's reversed again. You could have these little bits where it reverses for a little bit, and so. And we can observe this like in layers formed in volcanoes. So we're able to date them very accurately. So these are a record of time. But if we look at a seafloor spreading site, we see the same pattern. We see the same pattern of reversals on either side of the seafloor forming. Here's a short video about magnetic reverse.
Hi, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe how the reversals in Earth's magnetic field provide evidence for plate tectonics. Let's begin our discussion by establishing the fact that the Earth has a magnetic field. It's generated in the iron alloy of the Earth's core, but it penetrates through the mantle in the crust and wraps around the planet, leaving the South Pole and coming back into the North at the North Pole. This is important because this shape of the magnetic field ends up providing different conditions at different faces on the Earth. So if you were standing at the South Magnetic Pole, the magnetic field lines would be almost vertical, coming out of the Earth and pointing up. Whereas if you were standing at the equator, they'd be pretty much horizontal, parallel to the surface of the Earth. And if you were standing at the magnetic North Pole, they'd be pretty close to vertical again, but this time pointing down. This is important because certain rocks have magnetically susceptible minerals in them. So here we see a lava flow flowing along. On the Earth's surface, it's exposed to the Earth's magnetic field, and little magnetically susceptible minerals in that lava flow will align themselves with the Earth's magnetic field as long as the lava is liquid. Once it solidifies, they're locked in place, and geologists can collect a sample of that lava rock, take it back to the lab, and analyze which way those little fossil magnets are pointing. This allows the reconstruction of apparent polar wander paths for different batches of crust. So here on this map, we're looking at an apparent polar wander path for North America and one for Eurasia. So the way this is presented here, it's as if the continents cannot move. And if you go and you query North American rocks about where they were 500 million years ago, they say, well, the North Pole was here relative to us at that point. 400 million years ago, this is where the North Pole was relative to North America. 300 million years ago, it was here. 200 million years ago, 100 million years ago, and 0 million years ago, it happens to be at the North Magnetic Pole where it is today. Europe tells a very different story. If you go and ask Eurasian rocks, or their little magnetic minerals, where the North Pole was 500 million years ago, they give you a different answer. They suggest it was over here. 400 million years ago, 300 million years ago, 200 million years ago, 100 million years ago, but 0 million years ago, Eurasia tells exactly the same story as North America 0 million years ago. They both point to the modern North Magnetic Pole. So is this actually what happened? Were there two magnetic poles in the past that got closer and closer together over time? Well, an alternate interpretation is to allow the continents to move. And if you let the continents move around the face of the Earth, which of course is one of the suggestions of plate tectonics, then North America and Eurasia have the same apparent polar wander path. Another way that magnetic evidence from the Earth's core can help us decipher the mysteries of plate tectonics has to do with magnetic reversals. At certain volcanoes, you can go and look at the different layers of the volcano, with the older layers being towards the middle and the younger layers being draped on the outside. And you can find that in older layers, you have a normal magnetic polarity. In other words, the magnetic force is leaving the Earth's south pole and it's traveling around the Earth to re-enter the Earth at the magnetic north pole. But in other layers, you'll find a reverse polarity where the flow is reversed. It's leaving the magnetic north pole and coming around to the magnetic south pole. And then it goes back to being normal again. So it appears that the Earth's magnetic field flip-flops back and forth between these two stable states. This turns out to be a useful phenomenon to plate tectonics because of the concept of seafloor spreading. Remember this idea that continents break apart, they open up in a rift valley, and then if that rift valley gets thin enough and wide enough, it'll open up a new linear ocean basin, and that ocean basin will widen over time as the continents move apart from one another. As that new oceanic crust is forming at the oceanic ridge, it takes on the magnetic signature of whatever the Earth's magnetic field is at that time, either normal or reversed. And you can tow a magnetometer over that ridge crest, and you can record the different magnetic levels, which basically record whether or not that crust formed during a normal magnetic field or a reversed magnetic field. Here's an example, some real data from the Juan de Fuca ridge that separates the Pacific plate over here from the Juan de Fuca plate in here, which of course is subducting underneath the edge of North America. And you can see there are magnetic stripes there, basically normal and reverse polarity. Notice that on the left and the right sides of the ridges, basically the pattern looks the same. That's because the oceanic crust is being formed at an equal rate in both directions. So the overall summary here is something that looks like this. Continents separate and you get an oceanic ridge system. It ends up producing new oceanic crust that takes on the magnetic signature of whatever the Earth's magnetic field is at the time that it forms. And as the continents separate and you get more and more seafloor spreading, you get these stripes of normal and reverse polarity on either side of the oceanic ridge. This idea is corroborated if we look at the age of the oceanic crust. So if you go and you assess the age of the crust, which is based on small marine fossils that land in the sediments on top of that crust, you can see here a map for the age of the crust, and you see that the youngest crust is indeed located right there at the ridges. We've been able to work out a pattern of the Earth's magnetic reversals over time. So in the past 4 million years of geologic time, we've seen about 10 reversals of the Earth's magnetic field. White is normal and red is reversed. Here's a look at the North American plate, and if you go off to the east of the North American plate, you see the Atlantic Ocean. Let's pretend that we found a pattern of magnetic stripes over here on the oceanic lithosphere on the northwest of the African plate, and that we compared that pattern of magnetic stripes to our magnetic timescale that we just looked at. Say we figured out that this was 60 million years worth of crust. Say we found out that the easternmost stripe here was about 60 million years old. How far would you have to go on the other side of the mid-Atlantic ridge to find crust that's 60 million years old? If you answered exactly the same distance away, you'd be right. The same pattern of magnetic reversals should be observed over on the western side of that ridge. Thank you very much for your attention. This has been another Smart Figure.
So, by ocean drilling processes on the ship with ships, we can date the age of the seafloor. We can also observe paleomagnetism by dragging the magnetometer over the ocean floor. And we can examine a long fracture zones to sort of see this way that plate motion gets measured. So those are some of the ways we can measure like the history of plate motion. We can also measure it directly these days. So the original way the first way this was done was with things like very long baseline interferometry, where basically bounced a signal between two continents and measured the movement. These days you can do it with GPS. If you anchor GPS stations on each continent, you can actually observe the motion. It's something they actually have to correct for maps and global positioning things. It's a small correction, but it's there. And so you get this sort of movement in various places. This is some of the arrows show the amount of movement. Marked at the boundaries, you see the amount. This is not, none of this is very fast. The scale is in, an arrow of this length is 5 centimeters per year. So much of North America is moving less than 5 centimeters per year. The Atlantic Ocean is opening at something like around 2 centimeters a year. It's more down in the southern Atlantic. It's more like 3.5. The biggest places are over here. The East Pacific Ridge has got 15 and 13. You can see the numbers here at various places. But yeah, this is centimeters per year. So it's not very fast, but it builds up over long periods of time. So what drives the motion of plate tectonics? Well, there's no complete understanding yet. No one model explains all facets of plate tectonics. But we do know the driving force, the key to it is the heat of the Earth. Convection of the mantle caused by uneven heating. So when you have a fluid, which the mantle more or less acts like on long time scales, if you heat up parts, it becomes less dense, it will rise. When parts cool down, they'll become more dense, they will sink. And you get cyclic motion. So if you heat up a room from one side, heat will rise on one side and sink on the other. So convection is a type of heat transfer that involves the movement of a substance. So there's distinct convection occurring in the mantle, where warmer spots, you have magma rising, it cools, it sinks in other locations. And those currents help drive the plates apart or along. And additionally, there's forces from the crust itself moving. At the ridges sort of pile up as new material forms, and so they slide down along there. And then there's ridge push from the elevated position of the ridge, and then there's slab pull from the sinking slab at the subducting location. These are the forces that act on it. They're all sort of driven by a large scale convection in the mantle. Now there's several models that have been proposed. They're all based on convection of the mantle, but there's some debate about how much of the mantle is convecting, what parts are convecting, sort of. So the whole mantle convection models is based on the idea that descending oceanic crust will descend to a very great depth, and buoyant plumes will transfer heat to the surface from the boundary of the core mantle itself. So the convection cells in question are enormous. They go all the way from the boundary of the core and the mantle up to the crust. The other is the layer cake model, where there's multiple layers of convection. So the mantle is divided at some depth, and there are two zones of convection. There's an upper convection cell and a lower convection cell. The lower convection cell drives the upper convection cell, basically. So here are the two models. You have whole mantle model. The whole the convection cells make it all the way down to the edge of the core. The core heat is removed by plumes. It rises up at spreading centers, and then it sinks down again where oceanic crust subducts. And then the other is this layer cake model, where there's a much slower flow in the lower mantle, and the primary cyclic structure is in the upper mantle. We don't know which is the case yet. So that's the end of chapter 4. Any questions about any of that? Okay, I'll get started with chapter 5. Oops. Enable content. I forgot to do that. So we're going to talk about how we understand what's inside the Earth, since the deepest hole we've ever dug is only 12 kilometers deep, which didn't even make it through the crust. So we'll talk about earthquakes and the Earth's interior. So we'll sketch it, we'll go over the mechanism that generates most earthquakes. We'll compare and contrast the types of seismic waves and describe the principle of the seismograph. We'll explain how seismographs are used to locate the epicenter of an earthquake. We'll distinguish between intensity scales and magnitude scales, which do in fact measure slightly different things. We'll talk about the major destructive forces that earthquake vibrations can trigger. We'll locate where the Earth's major earthquake belts are. We'll compare and contrast the goals of short-range earthquake predictions and long-range forecasts. And we'll explain how Earth acquired its layered structure and name and describe each of the major layers. Because one of the things that earthquakes do allow us to do is look inside the Earth. So, what's an earthquake? Well, it's what it says in the name. It is when the Earth shakes. The ground shaking of the Earth produced by the rapid release of energy along faults. So an earthquake is when the ground shakes, when the Earth shakes, or when the Earth quakes. This is generally produced by the release of energy along faults. So this releases seismic waves, which are vibrations of the Earth itself, waves traveling through the Earth. We'll go over the various types. Some of them are kind of like sound waves. Some of them are not. Which is a form of energy that travels through the Earth. And there is a location where these vibrations, this release of energy starts. That location is called the hypocenter, or the focus. It's the point on the fault where slippage begins. It's the center of where the earthquake starts, where this energy release begins. This point is underground somewhere. And because faults can be at an angle, it's not necessarily where the fault meets the surface. The point on the Earth's surface directly above the focus or the hypocenter is called the epicenter. This is the plane where waves appear to start coming from on the surface. This is sort of the center of the earthquake. So if you have an earthquake, the earthquake is centered around the epicenter. The vibrations radiate outwards from the epicenter from the point of view of the surface. They actually started underground, but the epicenter is where they're going to hit the surface first because it's the point closest to the hypocenter. And they're going to look like they're spreading outwards from that location. So the hypocenter, or the focus, is underground. The epicenter is directly above it on the surface. So here you can see hypocenter, the focus. This is where the actual vibrations start. They radiate outwards spherically. They hit the surface first at the epicenter, and then along the surface, they go outwards in circles. The primary cause of earthquakes is movement along faults. So faults are just cracks in the Earth's surface where things can move. This is explained by the plate tectonics theory. And the mechanism for earthquakes was first explained by H. Reed. Basically, two sides of the fault are moving relative to each other, but there's friction between them. They're pushing together, so they stick. And when they eventually release, they vibrate, spring back due to a process called elastic rebound. So they start to move because they're stuck together, and then eventually that force overcomes friction, and there's a sudden release. And they spring backwards through elastic rebound, and vibrations occur as the rock springs back to its original shape, and it vibrates back into a new stable position. So you can think of it like snapping a stick in half. So the two rocks slide against each other, they start to bend, and they basically build up stored energy in the bending of the rocks on either side. And eventually that force between them overcomes the force of friction along the fault, and they suddenly release. And they snap, basically, and you get vibration like this, and they settle into a new stable state. But if the fault keeps moving, you can then get another earthquake later. So this is sort of the process of elastic rebound, how faults cause earthquakes.
Hi, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe why earthquakes occur and how they are related to faults. I'm going to go ahead and give away the answer right up front. Earthquakes are caused by movement along a fault surface. So basically, the fault is a break in the Earth's crust along which movement occurs. If that break makes it all the way to the surface, you might see it expressed as a fault scarp. The actual spot where the crust is moving is called the hypocenter, or sometimes it's called the focus. The spot directly above the hypocenter on the Earth's surface is called the epicenter. We can understand earthquakes better if we take a look at an analogy, and the analogy is the deformation of a stick. Basically, we're going to break a stick, and that's going to teach us something about how rocks deform along a fault surface. What we'll do is we'll start off with a stick, and we'll begin to add stress to it. So we're stressing the stick, but the stick is still stronger than the amount of stress that we've applied to it. In the same way, rocks can end up shifting relative to their neighbors and sort of warping and stretching and bending along a central zone of deformation. But when the strength of the rock or the stick is exceeded, then suddenly everything snaps. And you know that a stick is broken because you get this sudden jarring motion that goes up your arms. You hear a loud crack of energy going through the air. And the same thing is true in the earth. When suddenly the strength of the rock is exceeded, it will break and the blocks of rock will slide relative to their neighbors. As they judder along, it releases the energy that we feel as an earthquake. Now, after the earthquake, the crust returns to its original shape, but it's in a new offset position. Similarly, our stick has broken, but our stick has returned to its original straight shape. It's just now in two segments. So we start off with this movement occurring along the hypocenter. A little bit of movement takes place, then it sort of spreads out along the fault plane from that point. The rupture surface grows. And if you have enough of a rupture surface, it might intersect the surface of the Earth, and you end up developing a fault scarp. So the fault scarp is this surface right here where the actual surface of the fault plane is exposed. In this case, we have a dip-slip fault where the hanging wall block has moved down the face of the footwall block. So the footwall block is this big block of crust in the background. And you actually see the fault surface exposed here at the fault scarp. Notice that nowhere on this diagram does it say fault line. There is no such thing as a fault line. Faults are planes. They are not lines. If your fault intersects the surface of the Earth, but it's not dip-slip motion, but strike-slip motion instead, you get the surface expression as seen here. You have offset of these trees in this California orchard on one side of the fault relative to the other. All the movements taking place in the strike direction of that fault. That's a strike-slip fault. Here's another example in the inset photo of a fence that was offset along the San Andreas Fault during the Great California Earthquake of 1906. Okay, time for you to take a quick test. You're looking here at the Teton mountain range in western Wyoming, and you're looking at it from the perspective of Jackson Hole. So these horses are down here in Jackson Hole. All right, and you're looking up at the Teton range in the photograph. And what I want you to take a look at here is whether you think the Teton range in Jackson Hole is an example of a dip-slip fault or a strike-slip fault. Well, hopefully you said a dip-slip fault. That'd be right, because essentially you have a break in the crust along which the hanging wall has moved down relative to the footwall. As it's moved down, it's created some accommodation space that's filled in with all the sediments that make the nice flat surface of Jackson Hole. Meanwhile, the package of sedimentary rocks that lay atop the crystalline basement there has been mostly eroded off of the top of the Teton, so it's been stripped away by erosion. However, there are a few places where you can still see it. One is visible in the background of this picture here. You can see horizontal sedimentary layering there up at the top of that canyon. Thanks very much for your attention. This has been another Smart Figure.
So, because it's this release of energy, earthquakes are often preceded by they're preceded and followed by smaller earthquakes. So they're preceded by foreshocks, which are lesser magnitude earthquakes preceding the major earthquake. They're sort of little vibrations, little bits of looseness until the big release. And they're also followed by aftershocks, which are the Earth settling into its final position. There are lesser magnitude earthquakes occurring after the major earthquake. And they can actually happen months or years after a major event. This is where these big new blocks settle into their new position. And faults in large earthquakes are explained by plate tectonics theory. They're this sudden release of stress that's built up from plate movements. They are associated primarily with plate boundaries. You get earthquakes at boundaries between plates. Some of the largest earthquakes, so some of the most famous places for earthquakes are transform boundaries, like the San Andreas Fault, but some of the largest earthquakes are actually at convergent boundaries, because often the area of contact, so often where one plate is sliding under another, the contact area is big, the slope is shallow, and there's a lot of force there. So the release can be huge and massive. And these can lead to things like the tsunami that occurred in Indonesia a little while ago that was horribly destructive because it occurred, the earthquake that set it off was so close to the coast. So there was no warning. So convergent boundaries produce some of the biggest earthquakes because of the immense buildup of pressure. Transform boundaries can produce earthquakes along any of their numerous branches. And divergent boundaries generally produce small earthquakes because there's not that pressure buildup, because they're separating apart instead of coming together or sliding along side to side. So the world's largest earthquakes happen in megathrust faults, where the subducting plate slides underneath the overriding crust, and there's the shallow thrust boundary. And these megathrust faults are associated with subduction zones and continental collisions. And you can get enormous earthquakes here. So these are the thrust faults, smaller thrust faults, and then there's this subducting plane. So thrust faults occur with compression and at shallow angles. So it turns out that the waves from earthquakes are really useful. So seismology is the study of earthquake, and there are lots of little earthquakes all the time that aren't a big deal. Seismology is the study of earthquake waves, and a seismograph is a tool that records those waves. So seismography is the recording of earthquake waves. A seismograph is some tool that records earthquake waves. This records the movement of the earth. The record is called a seismograph. So here is a seismograph. The general idea is that you have some sort of weight suspended above the earth that's poorly, that's sort of decoupled from the earth, so that when the earth moves underneath it, it stays still. And then you have a rotating drum or some way to record the movement that's anchored solidly to the bedrock. And so as the weight stays still and the earth moves underneath it, there's a needle that records that movement on the rotating drum. That's the basic idea. And various seismograph-like things have existed for literally thousands of years. There's an ancient Chinese one that it was like this big bowl holding small balls in various directions, and it would spit out the ball in the direction that the earthquake was coming from, basically. So here's a video about seismographs and how they work.
Seismographs. Seismographs are instruments used to measure and record earthquake waves. The principle of a seismograph is simple. A heavy mass is suspended from a frame. When the earthquake waves arrive and the seismograph station starts shaking, notice that the frame moves back and forth, but the inertia of the suspended mass causes it to lag behind. The difference between these motions is recorded on the rotating seismograph drum. Notice also that it takes some time for the first earthquake waves to arrive at the seismograph station. If the focus of an earthquake is a great distance away, it may take several minutes for the first earthquake waves to arrive.
And that fact is a very useful one. And an even more useful one is that there are different types of earthquake waves, and they travel at different speeds. And this lets you figure out how far away the earthquake was from your seismograph. So, there are basically three types of earthquake. Earthquake waves can be split into two big types. They're body waves and surface waves. And the body waves come in two types. So you'll generally, if you're looking at a seismograph, you'll see three types of waves. You'll see two types of body waves and then the surface waves. So the body waves come in two types. There are P, primary or pressure waves. Both names work. They're generally just called P waves. These are like sound. They're compressional. They're push-pull. So here on a slinky, you can see if you sort of push the slinky forward and pull it back, you get sort of a pulse of compression that travels along with an expanded area behind. That's the kind of wave that's going on for a P wave. This is exactly the same type of wave that forms sound. So the sound you're hearing now is also a compression wave, a pressure wave. P waves can travel through solids, liquids, and gases. They go through everything because everything can be compressed. And they have the greatest velocity of all the earthquake waves. They're the fastest. Here is an animation showing what P waves look like in the Earth. So here you can see there's that compressed area traveling along. There's squished area, and then there's a spread out area behind it. So the wave, the vibrations are in the same direction as the motion of the wave. The other type of body wave is called secondary or shear waves. These are sort of a side-to-side shaking motion. It's a transverse wave, to use the technical term. They travel only through solids because they're based on like this shear motion where they're pulling on the next lump of earth along. And when they hit a liquid or a gas, they just slide. There's no resistance to shear motion, so they just slide. So at liquids or gases, they just stop and bounce off. They have a slower velocity than P waves. This means if you measure the difference in time between the P waves arriving and the S waves arriving, you can figure out how far away the earthquake was. This is incredibly useful. And if you do this at 3 places on the Earth, you can figure out where the earthquake started. So this is like a wave on a string, or a wave on a rope, or actually a water wave. If you shake the rope, you'll see the particles are moving up and down, while the wave is moving perpendicular to their motion. So here is an animation of S waves. So you can sort of see how if that hit a liquid, it would just slide at the surface of the liquid. And it wouldn't transmit into the liquid. And the last is surface waves, which are on the surface. They have complex, messy motion. They're the slowest of all the waves. And you can notice here, so we have the first P wave, then the first S wave, and there's a time interval of about 5 minutes, and then there's that messy surface waves. So surface waves actually do the most damage, because you can see they're much bigger And they're all on the surface in a very complex, irregular pattern. They're the slowest of the waves. They give us the least insight about what's going on underground because they're on the surface. Now, because waves travel at different speeds, we can use this to actually locate where earthquakes occur. So if we have seismographs from 3 different locations, what we can do is we can then, if we have 3 seismic stations that have recorded the same earthquake, each one will have a P wave and then an S wave later. We can use what's called the time travel graph to determine the distance the seismic waves have traveled. It's just based, you measure the difference between the P wave and the S wave, and you use a graph to look up how far away the earthquake was. You can work out the formula based on how S waves travel and how P waves travel. Now that you know the distance from each of your 3 seismic stations, you can draw a circle from each with the radius of the distance from each seismic station to the and where those 3 circles intersect will be the epicenter of your earthquake. So this is called triangulation. The circles will intersect at the approximate epicenter. And if you use GPS for anything, use this same idea of triangulation to find your location. The way GPS works is it figures out how far you are from several satellites orbiting the Earth, draws spheres, and where those spheres intersect, that is your location. It's a little different. It's based on the time it takes for light to travel from the satellite to your phone, your GPS detector. And it has to do a few tricks based on comparing the signals from a few different satellites. But then it can draw spheres, and with the intersection of those spheres, it can tell you your location on the Earth. So it needs 4 satellites to find you on the surface and like 5 to find you to also give you altitude. So here's an example where this is the first P wave, this is the first S wave. There's a 5-minute time interval. So if we look at how far P waves and S waves travel in miles after an earthquake, where they're 5 minutes apart, that tells you the distance you need to travel. And then you can do it again from Nome here. This is 1, 2, 3, 4, 5, 6.5. So 6.5. So it's like this far. So it'd be about here. So it's about 3,000 miles. And then Mexico City, that's only 4 minutes. That's right around here. And about, so this was around 3,000 miles, or maybe 4,800 kilometers. And then Mexico City is at about 3,000 kilometers. So you can figure out the distances from each of them. And then you can draw a circle of the appropriate radius for each of them. So 4,400 kilometers from Nome, 3,700 kilometers from New York, and 2,900 kilometers from Mexico City. And they all meet at the epicenter. And I think that's a pretty good place to stop. So we talked about triangulation to locate an earthquake. That's where you can find out where an earthquake is going to be.